All right, so we're going to be looking at the problems that we had up on the board. What we're talking about today are sequences and series. This is called a sequence because it has a certain pattern to it. Lizzie, I asked you guys to find the next three terms. What did you get for those next three terms?
I got 19, 23, and then 27.
Okay, were you able to come up with a formula, a sub n equals?
Would it be n plus 4?
Let's see if that works. This would be our first term. So this is a sub 1. This is a sub 2, a sub 3, a sub 4. So in this case, n is 1. So if we do 1 plus 4, that's not going to work.
Yeah, you're adding 4 each time.
Yeah, you are adding 4 each time, and I'll tell you 4 has something to do with the formula. What did you think, Zach?
4 and minus 1.
Okay, let's see if that works. So that would mean our first term, n is 1, 4 times 1 is 4, minus 1 is 3. Here's our second term, so n is 2, 4 times 2 is 8, minus 1 is 7. That works, doesn't it? So what do you think the relationship is with this 4? Why do you think that 4 occurs? Where's the 4 coming from? What are we doing every time?
You're adding 4 each time.
Adding on 4. So whenever we have some value that we're adding on every time, that's always going to go in front of that n. Then we have to figure out, okay, if it's 4 times 1, what do I have to do to that to get 3? Well, we're going to have to subtract 1 from it. So that's going to be a sub n equals 4n minus 1. And this is called the rule or the formula. This is what we're going to be looking at too today. All right, what about this one? What were our next three terms? What do you have on that one, Zach?
25, 36, and 49.
Okay, and what was your formula?
A sub n equals n squared.
Okay, and let's check that. 1 squared, 2 squared, 3 squared, 4 squared, 5 squared. Yep, that works. Good job. So this would be the rule for that one. Okay, what about for number 3? Max, what did you get for the next three terms?
21, 27, 33.
So what were you doing every time?
Adding things.
Okay. Did you come up with a formula?
No.
But what did we just say up above? Here we were adding on 4 and it was 4n. Here we're adding on 6, so it's going to have to be what?
6.
And then what do you have to do to 6 times 1 in order to get negative 5?
Minus
6 times 1 would be 6, minus 6, minus 11. Let's see if that works. So 6 times 1 is 6, minus 11 is negative 5. Let's try it on the second term. 6 times 2 is 12, minus 11 is 1 on the third term. 6 times 3 is 18, minus 11 is 7, so that works. All right, so this would be the general rule for it. Good. Okay, what about number 4 then? Number 4, let's see who's up. Henry, what do you have? Well, ignore the negative and positives. It's going 3, 6, 9, 12. Well, I don't even want to know that. I just want to know the next three terms, first of all. Okay, but what about the signs?
So negative 15, positive 18, and negative 41.
Good. All right, so those are the next three terms. Now, what we have to do on this one is ignore the negatives for a minute, because when the signs alternate, you have to do something special with that. But what are we adding on every time? 3. So it's going to have to be what? 3n. Do I have to do anything? 3 times 1 equals negative 3? Not quite, but it would equal positive 3, wouldn't it? 3 times 2 does equal 6. 3 times 3 is 9, not negative 9, but 9. 3 times 4. So now what we have to do is say that this is going to be times something else. And what it's going to have to be times is negative 1 to some power. Okay, so let's think about it. If I did negative 1 to the first, is that positive or negative? Negative 1 to the first. Negative. So that would make this negative, wouldn't it? What about to the second? Negative 1 to the second, is that positive or negative? Positive, so that would make that positive. Our third term would be 3 times 3, which is 9, times negative 1 to the third. What's negative 1 to the third? Negative. See how that would work for it? So anytime you want your signs to alternate, you're going to have to do this. You have to do -1 to the n. Now, what if instead of going this way, what if it had gone +3, -6, +9, -12, +15? What do you think, Nathan? To the negative n? Let's see if that would work. 1 would be -1 then, so -1 to the -1 is 1 over -1. That would still be negative. So it's not to the negative n. It would actually have to be to the n plus 1. Yeah, that would work. So if we wanted it to start positive, we'd have to do -1 to the n plus 1. So now this is the first term, but I would do 1 plus 1 is 2. -1 squared is positive. Second term. 2 plus 1, that's 3. -1 to the third, that's negative. So see how that would work for this situation. All right, so what about this one, the next terms? Nathan, what would be the next terms here?
81, 243, 721.
All right, were you able to come up with a formula? Okay, anybody have an idea on this one? When we're multiplying by the same number, that's actually, go ahead.
I don't know if this, I had a sub n equals 3 times a sub n.
You can't do that. You're getting onto something called a recursive function that we're going to talk about later. You actually could do that. If you said a sub 1 is 1 and you said a sub n is going to be 3 times a sub n minus 1, that would work. But we're really not doing that yet. We're doing what's called explicit, and this is called recursive. So let's think about this for a minute. Anytime we're multiplying, so we're doing times 3, times 3, times 3, times 3, that means it's going to be 3 to the n when we're multiplying by 3. It becomes an exponential, 3 to the n. But let's see if that works. Is 3 to the first 1? No. What's 3 to the first? What's 3 to the second? 3 to the third. You see what I'm saying? So this one doesn't work. How could I make it work? 3 to what power would give me 1? Go ahead, Henry. There you go. So if we do that, 1 minus 1 is going to be 0. 3 to the 0 gives us this. See, in this case, this is our first term, so n is 1. 1 minus 1 is 0. 3 to the 0 is 1. This is my second term. Plug in 2. 2 minus 1 is 1. 3 to the first is 3. So that all now works. That would be the explicit formula. Our book just calls it the rule. Okay? All right, get out your student journal and your calculators and turn to page 218. So a sequence, looking down here at the middle, rather than writing out the vocab, we're just going to read through it. A sequence is an ordered list of numbers. So it means that something's happening every time. A finite sequence is a function that has a limited number of terms. So it means that the terms stop. Like we might have 10 terms, 5 terms, whatever. Whose domain is the finite set of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, if we're going up to 10. The values in the range are called the terms of the sequence. So I have a sub 1, a sub 2, a sub 3, the fourth term. Okay, so we always use whatever the term is. If I say what's a sub 4, that means what's the fourth term. If I ask for a sub 10, that means what's the 10th term. An infinite sequence is a function that continues without stopping, so it goes on to infinity, whose domain is the set of positive integers. So this would be finite, 2, 4, 6, 8, 4 terms. Here's a sub 1, a sub 2, a sub 3, a sub 4. An infinite sequence, though, would have the dot, 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 meaning it goes on forever. A sequence can be specified by an equation or a rule. For example, both sequences above can be described by the rule a sub n equals 2n. See how we're adding on 2 every time and it ended up being 2n? Okay? All right. Let's have everybody try this now. What if our numbers had been 5, 8, 11, 14, ... What's that rule going to be? Give everybody just a second to think. Nathan, what do you think? And let's see if that works. For my first term, 3 times 1 is 3 plus 2. My fourth term, 3 times 4 is 12 plus 2. It works. Very good. How many people got that right? Just need a little more time, the rest of you, huh? All right, let's come up here now. The difference between a sequence and a series. A series means that we're going to be adding all the terms. Okay? So if we switch from a sequence to a series, we're going to be adding these terms. If we have an infinite series, it means it goes on forever. You can use summation notation to write a series. For example, if we're trying to write 2 plus 4 plus 6 plus 8, my rule is 2i, and we're saying that we're going from I equals 1 to I equals 4. This is saying to find the sum of all of those numbers. So 2 times 1, 2 times 2, 2 times 3, 2 times 4, from 1 to 4. That's what that means. This one we're still using the same rule. It's 2 times I. So it's 2 times 1, 2 times 2, 2 times 3. But now we're going to infinity, so we have to have infinity up there. All right, so for both of these, the index is I. Index just means what variable you're using. The lower limit of the summation is 1. The upper limit is 4 for the first one, infinity on the second one. Summation can also be called sigma notation because it's the same thing as the Greek letter sigma, written like this. If you've ever gone to a college visit and you've seen the fraternities or sororities, they're all Greek letters. Sigma is a common one that you see. All right. So there was a mathematician. His name was Frederick Gauss. He was born in 1977. He ended up being a very famous number theory mathematician. He also did a lot of work in science. There's a lot of science laws named after him. But he was always very, very advanced for his age. And there's a story about how when he was in 3rd grade, his teacher was tired of him always finishing his work so early. He'd be the one to say, oh, I'm done with that. I'm finished. I don't have anything to do. I'm done. And he was also kind of like a little bit overactive, a little hyper, I guess. So his teacher wanted to keep him busy. So she said, Frederick, I want you to sit down and add up all the numbers from 1 to 100. This is before calculators, no calculators. So she thought he would sit there and go 1 plus 2 is 3, plus 3 is 6, plus 4 is 10. She thought, okay, that's going to take him all day. It'll keep him busy. He came back within a few minutes, 5 minutes, this is the way the story goes, and he's like, the answer is 5,050. And she's like, I don't know, maybe. And he was correct. So the question is, how did he figure that out? Well, part of the thing about being really good at math is being able to find patterns. I'm going to write a little bit more to this pattern for you. Oh, wait a minute. I didn't mean to do that. Hold on. To do this. I was thinking we were only going to 50, but we're going to 100. So these were all the numbers he was adding up, and he noticed a pattern. Do any of you notice the pattern? Reagan, you look like you're thinking of something.
Well, you just have to add up the 10 and then multiply it.
Okay, that's a good idea, but I don't think that would quite work because if you went up to 10, the numbers are a lot,
Yeah.
they would be a lot bigger, wouldn't they, after that? So you want to know how he did it? Anybody have any ideas? It has to do with looking at this. What's 1 plus 100? 101. What's 2 plus 99? What's 2 plus 99? 101. What's 3 times 98? 101, right? What's 50 plus 51? 101. So how many pairs of 101 are you going to have? 50. So he already knew how to multiply, so he knew it was 101 times 50, and that's 5,050. And that's how he came up with it so quickly. So what he really realized then is he went on and he actually kind of came up with this formula for us. Actually, not that. He came up with this formula right here, this one. If we're trying to find the sum of the numbers from 1 to some other ending value, all you have to do is the number that you're going to have divided by 2, and then the number you're going to have plus 1. See how we had 100 of these? He did 100 plus 1. So he did 100 plus 1, that was 101. And then how many pairs of those was he going to have? Well, he had 100 divided by 2, which was 50. So this was the formula he developed at the age of, what is that, 7 or 8 in 3rd grade? So pretty amazing stuff. This one right here is a pretty common sense one. This is saying that if you're just trying to find the sum of the number 1, as say you go from 1 to 10, it's just going to be n, right? Because this would mean 1 plus 1 plus 1 plus 1, 10 of them. So it's going to end up being 10. This one is a little bit tougher. This would be if I'm trying to add up 1 plus 4 plus 9 plus 16 plus 25 plus 36. That's pretty hard to do, isn't it? I mean, it's not that bad, but we could type it in our calculator. But with this formula, it's saying if I want to find the sum, I can say what's n. Well, this is the same thing as the sum of, I'm going to use n instead of I, of n squared as n goes from 1 to 1, 2, 3, 4, 5, 6 terms. So using this formula here, it's going to be n, which my n is 6, times n plus 1, which is 7, times 2n plus 1, which is 13, divided by 6. And so really I can just do 7 times 13, which is 70, and 21, which is 91. So we can do that pretty quickly. Okay? Now, here's an even better thing that you're going to love. Get out your graph calculator. So on our graphing calculator, we actually have this symbol on there. So instead of even having to use that formula that I just used, go to your calculator and go under Math. Go up to Summation. If you have the summation, here's what you can do. I always just use x. You can use any letter. So I'm going to say x is going to go from 1 to 6 of x squared. Enter. And it tells me the answer is 91. Now, if you have an older calculator, you're not going to see the summation. How many of you are not seeing summation? All right, so you're going to have to do a little more work. See up on the board where I have that written out there? That's the way you have to do it in red. So you have to tell the calculator, I want the sum of the sequence x squared, my variable is x, and we're going from 1 to 6. So you have to type all that in yourself. The sum of the sequence x squared, my variable is x, from 1 to 6. Now, I'm going to do that on here. I don't know where sum and sequence are located. So I'm going to go to the catalog. See the catalog down here? Every single thing that we can do on the calculator, every operation is there. So I'm going to do second 0. I don't have time to scroll all the way down, so I'm going to jump to the S's. Here's my letter S. I'm going to do alpha to get down to the S's. Well, why didn't that work? There we go. I didn't push it hard enough. So now I can go down to the word sum. Hopefully it's on here. I think it is. There it is. So I'm going to have to do the sum. And now I have to find the word sequence. So I have to go under my catalog again. And I'm going to have to jump down to the S's at alpha S. You might have to do it twice. I keep having to do it twice to get the sequence. And now I have to do of x squared, here's the comma, x, comma, and then I have to say from 1 comma to 6 comma. And it's 91. So it's quite a bit more difficult to do the summation on the calculator if you don't have that symbol. If you need help with that, I can help you once we finish. All right, guys, let's go to the practice notes now. It says write the first 6 terms of the sequence. Anytime your book or this paper says 6 terms, we're just going to do 4. 4 is sufficient. So if we want to find the first 4 terms, we're going to plug in a sub 1, a sub 2, a sub 3, a sub 4. So you guys just tell me out loud, what's a sub 1 going to be? 0. A sub 2, 7. A sub 3, and a sub 4. Good. So there would be our first 4 terms. Okay, for this one, same thing. It can be written like this too. We're going to find f of 1, that's the first term, second term, third term, fourth term. Just substitute it in. If I plug in 1, 1 minus 1 is 0. What's anything to the 0 power? 1. 2 minus 1 is 1. Negative 2 to the first is negative 2. 3 minus 1 is 2. Negative 2 squared is 4. 4 minus 1 is 3. Negative 2 cubed is negative 8. So again, on your homework, if it says 6, just do 4. Also, if it says to graph, you don't have to graph them either. Just do the problem. Okay, in exercises 3 and 4, describe the pattern. You don't have to describe the pattern on your paper. You can just write the next term and then write a rule for the nth term. So look at this pattern. Negative 3, negative 1, 1, 3. What's the next number going to be? 5, good. So what did you do, Nathan, to get that? Add 2. So now we've written the next term. We need to write a rule. So a sub n equals. Anybody remember what we said we do if we're adding 2? It has to be what? 2n. Now how can I get negative 3 from my first term? 2 times 1 minus 5. Good. And there's going to be our rule for the nth term. All right, what about on this one? Change it to what I have. Make it go negative, positive, negative. Positive, negative, positive, negative. So on this one, what are we doing every time? We're adding on how much? 2/5. Okay, so if I add 2 more 2/5, and I just pretend like this is positive, when those signs alternate, that's what we have to do, that negative 1 to the n. So what's this going to be if I add 2/5 to positive 8/5? Or just 2 even, right? There's my next term. So my pattern then is, we just said it's going to be 2/5 in, because we're adding 2/5, but we're going to have to do negative 1 to the, what? Is it to the n or to the n plus 1 to make it start positive? N plus 1. I always like to put the negative 1 in front of this. I just think it makes it easier. Okay, write the series right here using summation notation. Summation notation is where we use the sigma. So we know our sigmas, we're always going to start at 1. I always like to use n's instead of i's. Are the signs alternating? Yes, so I have to do negative 1. Does negative 1 to the n make them alternate correctly? Negative 1 to the first, would that make it negative? Negative 1 to the second, make it positive? Okay, so that's fine. If it goes dot, 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 what's going to go on top? Where am I ending? Infinity, good. Now what's happening to 1, 2, 3, 4, and 5? They're getting squared. So that would be our answer in summation notation. All right, and then 6 and 7, these would just be the type that you would put in your calculator. I think you're fine if you have the newer version. I'm going to show you if you have this older version. If you already have this up, guys, you don't really have to type it in again. You can do second enter, and now you can just go back and edit. You got to be careful with this, though. This is kind of tough to edit because I'm going to have to delete these, and I'm going to have to insert. So I'm going to have to insert x divided by parentheses x minus 1, and I want to get rid of that right there. That's the way I would have to type it in. See what I'm doing? The sum of the sequence of x over x minus 1, my variable's x, I'm going from 1 to, oops, I'm not going from 1, I'm going from 2 to 5. I get that answer, I math frac it, 73/12. Just to double check that we put that in right, I'm going to do second enter, and I'm going to go up to my sigma. I'm going to change this. 2 to 5. Oh, well, I'm just going to retype that in. It's easier just to retype it. So we're going from x equals 2 make sure you use parentheses around that denominator if there's more than one term. Okay, 73/12. And this one would be done the same way. This is actually easier to type in than the other one was. All right, any questions? Okay, so you've got your green sheet. You know what to do for homework?